What's up, everyone? So this time we're going to look at the function y equals f of x. Again, we use x our variable, so you can just call it however you want, g of x, h of x, however you want. But y will be our dependent variable, and this function is equal to sine of x. And again, x is our independent variable, so good. But again, we're not going to use any calculus, or we don't need to use any calculus techniques that we have already learned in calculus class this time. All we need to do is a quick review of pre-calculus class material. And since we're talking about something that we can do up to calculus course, so of course our codomain again is the real number as well. So we only consider both x and y, the two variables within the real numbers or real lines. So again, we're going to use the graph at the end to help us to try to check our answers. So we're going to use all the knowledge that we have learned in pre-calculus course to help us finding the domain, the relative extrema, even though the term has not been mentioned until in actually calculus 1 class, and as well as the absolute extrema, and finally the range of this function y equals sine of x. And again, before we move on and go to the solutions, you can pause the video and try yourself first, and then go back and see if you actually get the same answer as I do. Are you ready for it? Here we go. So, as we know, sine is one of the regular trig functions, or the basic trigonometric functions that we have. And if we consider the function itself, even without the graph, we know that the domain has to be all real numbers. And again, how do we know that? Because as we consider the definition of the sine function, we can use the unit circle, and in fact, it's easier to draw a circle before you mark it. That will be actually more precise. But anyway, pretend it is a unit circle, meaning that we have the radius 1 here, and then we're going to consider the angle here. Usually we use theta, and then here is the two sides, A and B. I'm going to use A and B instead of x and y, so that we don't get confused with this function here. But then, how do we determine the sine of the angle using the unit circle? Well, we know that by definition, sine of an angle is opposite of opposite over hypotenuse, where the hypotenuse is just the radius, which is equal to 1 here. And then for the opposite side, we have here the vertical length, and this vertical length is actually the value of the second coordinates. Let's call it b here. Okay, and then of course the horizontal will be a. So in fact, we have the sine of the angle theta is equal to b. So now we can just replace the angle from theta to x, so that we're going to match with this function here. And as we can also see that we can, as long as the angle goes over one cycle like this, we end up with 2 pi radians, but that is going to give us the same value as a 0, and we can actually go backwardly as well. Negative 2 pi radians is going to end up with the same result as what we have, meaning we can add as many 2 pi as we want, or subtract as many 2 pi's as we want, so that there is actually no boundary of the angle that we can choose. It is not bounded between 0 to 2 pi radians anymore. We can extend it to any real numbers. And therefore, since the angle can be any real numbers, we are saying that the domain of this function, which is actually referring to the angle on the unit circle, could be any real number. Good. So next, what's the range? Range is actually the easiest to check as well, because again, we're going to use the unit circle, meaning that if we're going to go by the definition here, the range would just be the positive b values on this unit circle, which means we can look at the highest point on the unit circle and the lowest point. And we see that the highest point is here, where the b value is equal to +1, and the lowest point will be down here, and the b value is -1. And since the unit circle is also continuous, meaning that we can choose any b value in between -1 to +1, and we'll always be able to find a point on the unit circle that's satisfied with the b value equals to something that we chose. Therefore, what's the range? The range is just from -1 to +1. And again, do we include the two endpoints this time? Yes, because we definitely can find a point such that the b value is -1, which is actually down here, as well as a point where the b value is +1, which is up here. So we have to include those two endpoints. Good. Now, how do we find out the relative maximum and relative minimum, as well as absolute maximum, absolute minimum? We know that absolute maximum and absolute minimum will be at -1, at +1, and when y is equal to +1 and y is equal to -1 respectively. And then for relative maximum and relative minimum, if we think of the graph of the function, of course, we see that the y value of the relative maximum and relative minimum will be +1 and -1 as well. But those are not the complete answers, because again, when we try to find the relative extrema and the absolute extrema, we need to think it as a point, meaning we need to have both x and y values instead of just the y values of the function. So since we know that the y values would be at +1, we'll write here, and then here is -1, and we also get -1 here, +1. So the question is, how do we find out the x values? Okay, so first of all, absolute maximum and absolute minimum will be the two extreme endpoints in the range. So those are definitely true, and we will not be able to find other values. So how do we find the x values? Of course, we're going to substitute back into our function. So now we have to consider sine of x equals y. And to find out the absolute maximum, we set y equals 1 and solve for x. So x will be, we can use the unit circle to help us if we don't like using the arc sine or the inverse trigonometric function to help us finding it. So when would the angle be when would the sine of the angle giving us 1? On the unit circle, there's only one point, which is up here, right? And the angle right here is from the positive x direction to positive y direction, or positive a direction to positive b direction. We turned 90 degrees, or pi/2 radians. So we get x is equal to pi/2. But wait, we are saying that x is not just bounded between 0 to 2 pi. We have to consider the whole real line. So since we can actually get cycle here by adding 2 pi or subtracting 2 pi, or multiple copies of 2 pi's, meaning that we have something what we call periodic if we try to look at the graph. And when we consider that one point is actually including many different values. and in fact is actually got overlaid every time when we rotate the angle by 2 pi. So we have to add multiple copies of 2 pi, or we call it 2 pi n, 2n pi, however you want it, where n is any natural numbers. Good. So let's write down the answer first. So for absolute maximum, or absolute maxima, they are located at pi over 2 plus 2 pi n, and here we're going to write a note, usually aside, but then we're going to use this for all the answers anyway. So here is the note. N is all as any integer. Could be positive, could be negative, could be 0. So good, we found the absolute maxima. And how do we find the absolute minima? We're now going to replace the 1 by -1. So we have the points down here. When is this true? If we rotate counterclockwise, we get 3 quadrants, which is 3 times of pi over 2, meaning that we end up with 3 pi over 2. And then again, it actually includes infinitely many copies, and we can get those copies by adding multiples or subtracting multiples of 2 pi. So we actually get 3 pi over 2 plus 2 pi n, comma -1 for our absolute minima. Great. So next, we claim that the relative extrema are actually all the absolute extrema, and there is no other points that could be our relative extrema. So if we go back and think of the graph of the function, this is true, right? How do we actually prove it? So now we need to secretly throw in with the idea of the use of derivative again. So again, to find out the relative extrema, we can just take the first derivative of the function, especially this is continuous, it's very easy to do. So if we take the derivative, we're going to get cosine of x. So we have the cosine of x, so that we are now going to set this equal to 0. And again, for Calc 1 student, you probably don't know the derivative of the trig functions yet, so this is actually a boil for something that you will first learn in Calculus 2. Anyway, now we take the first derivative of the function and set it equal to 0. Next question is, when is this true? Again, we can just use our unit circle to help us finding it. Or 0 is one of the special values that we need to memorize. So we can just think of what angles we have to get for this result. So we end up with 2 different results. One is on top, one is on bottom. For both of them, the vertical value is 0. And when would this happen, or what angle will make it happen? Again, we're going counterclockwise. So we end up with pi over 2 for the one on top, and then on bottom we have 3 pi over 2. Okay, so I'm going to split it into 2 different answers. And again, why do we have to leave this much space? Because each point is always referring to infinitely many copies on the unit circle. And to find out other copies, we just need to add or subtract multiples of 2 pi. So again, we end up with this and this. And therefore, we can now say that we found all the relative extrema. Because again, this is a continuous function, and then there's no sharp turn. In fact, this has no sharp turn. So we can say that we don't need to consider any other cases, and this is everything that we have after we take the first derivative, meaning that this will actually give us everything that we need for relative extrema. Then again, we then need to check the cases so that we know which one is going to give us what y value. When x is equal to pi over 2 or plus 2 pi n, the y value is sine of x, which is same as, again, this 2 pi n is not going to contribute anything inside the sine function, because again, that's just telling us that that's the multiple copies of the same point. So we can just ignore it when we substitute in, so that we just get sine of pi over 2, and then again the plus 2 pi n. You don't have to write it here, and it will give you the same answer anyway. And on what sine pi over 2? Positive 1 is the point up here. So we just get that the relative maxima would be the absolute maxima, pi over 2 plus 2 pi n. And if we substitute for the other one, which is going to give us the negative 1, and that will be our relative minima, 3 pi over 2 plus 2 pi n. Okay, and you might ask, well, how do we know that those must be maxima and minima respectively? Because now, go back to what we have already found, the absolute extrema. 1 is always the highest value that we can get for y, meaning that if we have this point, there's definitely no other points around the point, this point here, that can be higher than it, meaning that this will be the highest point locally. Similarly, this will be the lowest point locally for each n. So we can conclude that when we have y equals positive 1, that will give us the relative maximum, and when y is equal to negative 1, that point will definitely be the relative minimum. Good. So we found all the values and all the answers. Last, we're going to check the graph of the original function, y equals sine of x. So again, we're going to graph the function out. We have positive 1 here, negative 1 here, and then we have all the key points. There are way too many, so I'll just plot a few. Right here, we have the multiple copies of pi over 2. And we also need to have those in the negative direction. 3 pi over 2, and we have negative 2 pi. So where are the points when x is equal to multiple copies of pi over 2? Well, those are special values. I hope you have all remembered those. When x equals 0, y is of course equals 0. And when x is multiple copies of pi, y is always equal to 0. So we're going to label those points. Next, when x is equal to pi over 2, we get y equals positive 1. And that is actually what we found. Similarly, we can find out that when x equals negative 3 pi over 2, again, that's just this minus 2 pi, y is equal to 1. And more importantly, we say that sine of x, or the sine function, is periodic, meaning that the shape of the graph will actually look the same in some period. So in this case, it will look the same when we shift by 2 pi, meaning that if we add 2 pi or subtract 2 pi, the points will actually locate at the same height. So we will also get when x equals 3 pi over 2, we have y equals negative 1, so somewhere around here. And again, because of the periodicity, we have the points down here when x is negative pi over 2, which is 2 pi less than the points that we found. Good. So we just now need to connect the points to give us the graph of the function. How does that look like? Well, it looks like this. Remember, it's periodic and it should actually turn better here, and as well as here and here. We'll hit down here and up here, and they're all connected, continuous, like this. So if we look at the graph, we see that we can continue on the x direction for both positive and negative side, and it will never end because there's no x values that cannot give us any y values. So number one, the domain, check. Next, let's check the range. We see that it keeps going up and down, and we say that is periodic and is actually get bounded because since it's periodic, once we have some highest point inside of the period, as we shift by 2 pi, that point will still be the highest, and then the height will still be the same, and similar to the lowest point. So as we see that y equals 1 is the highest point at some x values, and there is no x values inside of the period that we're looking for. And let me box it with the green color. Okay, we're saying that the period of the trig function sine of x is has a period of 2 pi, meaning that for every 2 pi we will actually see the same shape of the graph again and again. So we just, instead of looking at the whole graph, we can just look at the graph inside of the period, which is inside of 2 pi here, from 0 to 2 pi. And as we see inside of it, the highest point is the point at y equals 1. So that's going to give us that's the highest point for the whole graph is also be equal to 1. Similarly, we can argue that the lowest point is -1 inside of the box, meaning that the lowest value of the whole graph will also be at at y equals -1. So the range is from -1 to +1, including the two values that we have. Check. And then for absolute maximum, absolute minimum, we're just substituting back in, and then we see that inside of the period there is one maximum, one minimum, and that maximum will actually get copied into another period. So we will be able to get the absolute maximum as well as the absolute minimum. Great. Last, the relative extrema. Again, now we just need to look at the local part of the graph inside of the whole graph, the graph globally or entirely. So we just need to look at these 2 points. And this point is going to give us a maximum locally. This point is going to give us the minimum locally. So we get the relative maximum, relative minimum, and as we make the copy and do the shift, we actually get the maximum and minimum again. And you might ask, how about the endpoints inside of the box? Well, usually we need to consider of those points too, but don't forget, just because we're looking inside of the box doesn't mean the domain is just inside of the box. We need to look at the whole domain. So if we try to move that copy and then bring it to somewhere else, such as here, if we're going to shift the box by -2 pi by 1 period to the left, and consider the point when x equals 0, now we see that is no longer the minimum, because when we look at the graph locally, we can find some other points such that around it, such that the point is lower than when x is equal to 0. So that is no longer the lowest point inside of the region that we're boxing. So we can use the same argument for 2 pi here. If we extend the graph, if we move the box and extend the graph, we can find another point up here that is a little bit on the right of x equals 2 pi. So that new point in blue is actually higher than the point when x equals 2 pi, and makes that x equals 2 pi is no longer the highest point inside of the little circle. Good. So we now see that why these two cannot be considered as the relative extrema, meaning that the only possible relative extrema inside of each box will be either the peak or the valley down here. And therefore, we just get all the copies of relative extrema. That's it. This one is a lot shorter than the previous one, and at least I didn't have to break it into 2 parts this time. And perhaps you may ask, why do we have to do this function on a sudden after we did something that's a little, well, or maybe very complicated to you? That's because now we're going to step in and do the last parts for this short series. And for the final function that we're going to look for, it will be a mix or kind of like a fusion of the 2 functions that we have done. So at that time, we're going to use all the techniques that we have done so far in up to calculus 1 to find out all the terms that we want to find, the domain and the range, as well as the relative extrema and the absolute extrema. All right, that's it for this video. I hope you all enjoyed this. Please don't forget to like, and don't forget to subscribe either, so that you can find out more of my other videos. And if you have any comments or thoughts or some ideas, you can leave your words below in the comment section, so that I'll read it and answer it for you guys. And I'll see you guys in the next video.